A common effect on a communication channel is noise being added to the transmitted signal so that the received signal is the sum of the transmitted signal plus the noise. So when we have a transmitted signal such as these red pulses here, which is basically in this case a polar line code, that's our transmitted signal, which we denote as X. The received signal Y is the sum of the channel noise and the transmitted signal. So the received signal Y would look something like this blue waveform, which is the sum of the transmitted signal, that is the pulses, to which the channel noise that gets added. So the received signal Y is equal to the transmitted signal X plus noise. Now, we know pretty much about the transmitted signal because we designed the transmitted signal the way we want it. But the channel noise is random, and we need to understand a bit more about the characteristics of this noise. And as we have discussed in the previous lecture as well, the noise that we are dealing with here is Gaussian noise. It is random with the Gaussian distribution, and we also describe what do we mean by white noise. So white means it has frequency components covering the entire frequency spectrum, and at each of the frequency value the magnitude or the power of the noise is the same. So the power spectral density of white noise is flat, and it's additive because it gets added to the transmitted signal. Now, the Gaussian distribution was described earlier as well in the previous video. So let me rewrite that. Gaussian distribution is something like this. For noise P of n, so it gives us the probability that the noise takes on a certain value, and it is given as 1 by sigma square root of 2 pi e power minus half into n minus the mean mu by the standard deviation sigma, the whole square. So that's our representation of the Gaussian probability density function. Now, let us also elaborate what is mu. Mu is the mean value of the distribution, and sigma is the standard deviation. And as you are aware, the square of the standard deviation, that is sigma square, is nothing but the variance of the distribution. Okay, we had touched upon these topics in the last lecture as well, but we'll go into more details of the Gaussian distribution itself, and we'll try to understand the noise that we are dealing with so that we can devise a mechanism for the receiver in order to combat that noise and be able to detect what was transmitted with as few errors as possible. Okay, that's the whole objective, because what we transmit is a clear pulse waveform, but what the receiver gets is a distorted version of the pulse waveform. So the amplitude is not constant during the symbol interval, but rather it has random fluctuations around the transmitted voltage value. So the job of the receiver is to detect is to observe the received signal, which is distorted by noise, and determine whether the correct symbol value that is being represented by that voltage level. Okay, if it's a binary case, it has to determine whether it's a 1 or a 0, and we could also have the MRE case where we have not just two voltage levels, but we might have multiple voltage levels as well. Okay, now the next thing we are going to focus on is to understanding what does this mean value represent, and we'll see both in the time domain as well as the PDF of the Gaussian distribution, and see how changing the value of the mean affects the noise waveform as well as the distribution or the PDF of the noise waveform. So what we have here on our screen now is the noise waveforms of three different Gaussian distributed signals with different values of mean. So if you notice here, the mean value for the blue waveform is 0. The mean value for the red waveform is -2, and that for the black waveform is +2. All of them have the same standard deviation of 1. So we are going to see the effect of changing the mean value. And you see here, by mean value, it's we mean the central value around which all the noise signals amplitudes are going to be distributed. So it is centered on the 0. So around the 0 there are some positive values and there are some negative values above and below the 0, which is the mean value for the blue waveform. If you look at the red waveform here, which has a mean value of -2, you see that the red waveform is centered on the level of -2 volt, right? So you have some values above -2 and some values below -2. So if you take the average of all those samples for a sufficiently long length of the signal, you would get an average value of -2. And similarly, the black waveform has a mean value of 2. So the waveform is centered on +2 here. So there are some sample values which are above 2 and some which are below 2, and the average, when you add and take the average all of them, then you'll get an average of 2. So in the time domain, from the waveform perspective, we see that changing the mean value kind of shifts the waveform up or down depending on the mean value. If it is 0, it is centered on 0. If the mean is 2, that means the waveform has got shifted up by 2, because the mean is now +2. And if the mean is -2, the waveform has got shifted down. Obviously they're not the same waveforms, but they have the same statistical properties in terms of their distributions. Okay, so that's the interpretation of the mean value. And what we observe is that changing the mean value means changing the DC level of the signal, that is, the waveform gets shifted up or down along the voltage axis. Okay, now let's have a look at the probability density functions, which are at the bottom, in the bottom part of the plots here. So the probability density function corresponding to the blue waveform, which has a mean value of 0, we see it's a bell-shaped curve which is centered on 0. So that's the mean value of the blue colored waveform. So let me write it in blue. So that's mu equals 0, because you see here it's centered on 0 here. The central value is 0 where the peak occurs, right? And similarly for the red waveform, the central value is -2. So the mean value of this distribution here for the red PDF is -2, corresponding to this waveform here, the red waveform. All right, so the mean is mu equals -2 for the red PDF, and for the black PDF the mean is +2. So mean equals +2. So as you see here, this black PDF is centered on +2. All of them have the same standard deviation, and that's why the width of all of these PDFs is the same, right? And another observation that you need to make here is that the Gaussian PDF is symmetric about the mean value. So if you take the mean value as the central point, then the left hand side and right hand side about the central value or the mean value are mirror images. So the Gaussian PDF is symmetric about the mean value. So for the blue PDF it is symmetric about 0. For the black PDF it is symmetric about 2, because the mean value is 2. And this red PDF is symmetric about -2, because the mean value is -2, right? So that's the implication of changing the mean value of the Gaussian distribution. Basically, if the mean is changed, that means the central parameter gets changed and the PDF gets shifted. So if you look at the PDF for mu equal to 2, is the same as the PDF for mu equal to 0, but it is shifted to the right by 2. Similarly, the red PDF is the same as the blue PDF, except that it is the shifted version to the left by -2, right? So now, given these PDFs, we can now represent or write down the equations for each of these PDFs. So we'll start with the blue PDF, which has a mean value of 0 and a standard deviation of 1. So we'll substitute sigma equal to 1 and mu equal to 0 in this general equation of the Gaussian PDF, and we will get the PDF for the 0 mean Gaussian distribution with the standard deviation equal to 1. So the PDF corresponding to the blue PDF or the blue noise waveform is 1 by sigma is 1, so we can leave it out. So it's 1 by root 2 pi e power minus half, and the mean is 0 in this case, so it's n minus 0 by 1 the whole square. So it is simply n square. N minus 0 by 1 is n, so minus half into what happened here? Okay, I'm just resizing the screen. Okay, minus half into n square, so we can simply write that as minus n square by 2. So that's the PDF for the Gaussian distribution when the mean is equal to 0 and the standard deviation is equal to 1. And in such a case, this is also called as the normal distribution. So the normal distribution is nothing but the Gaussian distribution with mean mu equal to 0 and standard deviation equal to 1. So we call this as normal distribution. Next, let us write the PDF equation for the black waveform, which has a mean value of 2 and standard deviation equal to 1. So we will have it as P of n is equal to 1 upon sigma. Sigma is 1 here, so we'll have 1 upon root 2 pi e power minus half, n minus the mean value is 2, so it's n minus 2 by sigma. So sigma is 1, so we don't need to write the denominator there, so it's divided by 1 the whole square. So that's the PDF expression for the Gaussian PDF with mean equal to 2 and standard deviation equal to 1. And similarly for the red PDF, we can write the probability density function P of n as 1 by sigma root 2 pi. So sigma is 1 into root 2 pi e power minus half, and it's n minus of minus 2 because the mean value for this is minus 2, so it will become n plus 2 by sigma. Sigma is equal to 1, so we can leave it out, the whole square. So those are the expressions of the Gaussian PDFs for different mean values. So when the mean value is 0 and the standard deviation is 1, we call it as the normal distribution. It's called the standard normal distribution, and it's an important distribution in real life. Okay, and all of these PDFs have the same standard deviation, which is equal to 1, and that's why you see that the width of the PDFs or the spread is the same in all the cases. Another way to interpret, or to observe the standard deviation is to look at the variation from the mean value. So the standard deviation gives us by how far the samples are going up and down, above and below the mean value. If the standard deviation is high, you will see that these will fluctuate more. That means there are samples further away from the mean value. So if the standard deviation is less, that means all the samples are very close to the mean value. If the standard deviation becomes higher, that means the samples or the voltage levels or the amplitude levels of the noise samples would be distributed further away from the mean value. That means it will have a much higher peak to peak range. That means the noise signal's amplitude will have a bigger peak to peak, as we will see shortly. So what I have shown here in this plot is the Gaussian waveforms or random waveforms with the Gaussian distribution for a fixed value of mean. So the mean value is fixed. All the three waveforms have the same mean, which is centered on 0. So the mean is 0, but all of them or each of them has a different standard deviation sigma. So the blue waveform has the smallest standard deviation, which is equal to 1. So you see that the blue waveform has the smallest peak to peak range of the three. Then the red waveform has standard deviation of 2. So the red waveform has amplitudes which are further away, which are oscillating further away from the mean value or fluctuating further away from the mean value. So the red waveform has a bigger peak to peak range than the blue waveform. So that is what we mean by the standard deviation, how far the samples are actually distributed away from the mean value, right? So the red waveform has a higher standard deviation as compared to the blue waveform. And the black waveform here, as you see, it has an even bigger peak to peak range because it has the largest standard deviation here, you see. So the mean value is still 0, so it is centered on 0, but the fluctuation around the mean value is much bigger. So the samples are distributed further away from the mean value. So there are bigger spikes of the noise, right? So if the standard deviation of the noise is more, that means you're going to have much bigger peaks for the noise signal amplitude. So that's the observation in terms of the standard deviation for the random signals which have a Gaussian distribution. So the implication is that if the standard deviation is high, that means the signal will have a higher peak to peak range. If the standard deviation is low, the signal will have a very small peak to peak range. Okay, and the corresponding PDFs, if you see here, all of them are centered on 0 because all of them have the same mean. So the mean value for the blue, red as well as the black PDFs, they're all centered on 0, and that corresponds to the mean value. So all of them have the same mean. So let me write with a general color, because they all have the same mean, mu equal to 0, but the standard deviations are different. So if the standard deviation is different, the PDF is narrower. As the standard deviation increases, the PDF kind of spreads out, so it becomes wider and wider. What this means is, if you look at the blue PDF, which has the smaller standard deviation, it means that most of the signal's amplitudes are lying between the range, let's say, from -2 to +2. They are in the range of -2 to +2. Most of the signal amplitudes are in that range, between -2 and +2. Any value greater than +2 or less than -2, it has a very small chance of occurring. It occurs very rarely, but most of the time the signal is lying between that range of -2 to +2 volt. And if you look at the red PDF, you see that most of the time the signal, let's say maybe it's between -3 and +3, right? For the same level, if I take here, so it's somewhere between -3.1 to +3.1. So the signal amplitudes have a higher probability of being higher values. The noise amplitude to be higher value has a higher probability. And for the black PDF, you see that it's even more spread out. That's why we see that it has a much bigger peak to peak range. So you need to be clear about what we mean by these parameters of the Gaussian distribution, because these are what define the characteristics of the noise that we are going to deal with. So like in the previous case, we can write the expressions for the Gaussian PDS for the three signals here. All of them have the same mean value, but their standard deviations are different. So for the blue waveform or the blue PDF, the distribution can be written as 1 by, the standard deviation is 1, sigma is equal to 1, root 2 pi e power minus half into n minus, the mean value is 0, so for all of them, so it's simply n square n minus 0 by sigma. For the blue signal, the standard deviation is 1, so it's simply n square by 2, right? So that would be the PDF for the blue waveform, right? The blue PDF, which is nothing but the normal distribution. For the red waveform, the PDF expression would become P of n to be 1 by the standard deviation in this case is equal to 2, so 1 by sigma is 2 root 2 pi e power minus half into n minus mu by sigma the whole square. Mu is 0, so n minus 0 by sigma is 2, so n by 2 the whole square. So that would become our PDF corresponding, the expression for the PDF corresponding to this blue distribution, the red distribution. And then for the black distribution, which has the highest standard deviation, we can write the PDF as 1 by the standard deviation is 3, sigma is 3 root 2 pi e power minus half. It will be n by 3 the whole square. So it's n minus 0 by sigma the whole square. So those are the expressions of the PDFs when you have the standard deviation to be changing and the mean value is fixed at a certain number. So whatever is the mean value and whatever is the standard deviation value, you can substitute them in the general expression, and you can write down the expression for the corresponding PDFs. Well, now, the next thing you need to understand is what do these PDFs actually tell you. What these PDFs tell you is that it tells the probability of having the noise amplitude to be any of these values. So what is the probability that the noise signal amplitude is 0 volt? For this blue PDF, when the mean is 0 and the standard deviation is 1, it indicates that the probability that the noise amplitude is 0 volt is 0.4. That means it's around 40%. For 40% of the time, the noise amplitude is going to be 0. And what is the probability that the noise amplitude is going to be 1 volt? So it's around this value, which is, let's say, 0.25, right? Approximately, or 0.24. Similarly, for minus 1 volt, it's also around 0.25, and so on. So we can interpret what is the probability of the noise having a certain amplitude, or the noise signal having a certain amplitude. So depending on the mean and standard deviation of the Gaussian distribution, we can now know what is the probability that the noise is going to have a certain amplitude or a certain voltage level. So you see that for the red case, the probability of the noise amplitude being 0 is 20%, which has reduced from 40%, right? So that means instead of 40% of the time the noise amplitude being 0, we will now have only 20% of the time that the noise amplitude will be 0. And that's because the noise signal is having a much bigger fluctuation around the mean value as compared to the blue signal, right? So, and for the black PDF, which is having an even higher standard deviation, we see that the probability of the noise signal being having 0 volt amplitude is reduced even further to about, let's say, 12 or 13%, as compared to 20% when sigma is equal to 2 and 40% when sigma equal to 1, right? So that means there is a higher probability that the noise is going to have an amplitude which is of a higher value when the standard deviation is more, right? Okay, So now let's put everything together, and we'll see and just summarize this very quickly. So when we have the mean value changing, what we notice is that the PDF gets shifted left or right. So the PDF of the Gaussian distribution gets shifted either to the right or to the left, depending on the mean value of the distribution. And when the standard deviation is changed, the width of the distribution gets changed. So if the standard deviation is small, the width of the distribution is much narrower, and if the standard deviation is larger, the distribution gets spread out even further. And the implication is that higher values have of noise have a higher probability of occurrence. So if we compare, let's say, the probability that the noise amplitude is, let's say, 2 volt. So for the blue PDF, the probability of the noise amplitude being 2 volt is around 5%. So at this point, so 2 volt is around 5%, which is 0.05, right? The probability is 0.05 or 5%. For the red PDF, the standard deviation, the probability that the noise amplitude is 2 volt is around, say, 0.14 or around 14%. And for the black PDF, it's around 10%, right? So 10, just over 10, so around 11%. So as we keep going further, we see that when the standard deviation is higher, the probability of the higher amplitudes of the noise becomes higher. So for example, 4 volt here, the blue PDF or the blue noise waveform has the smallest probability of the noise being 4 volt, and then the red PDF or the red waveform has the second highest probability of having the noise amplitude of 4 volt, and the black waveform, which has the highest standard deviation, has the highest probability of having a noise amplitude of 4 volts. So you see that as the standard deviation increases, the probability of higher amplitudes for the noise voltage becomes higher. The next thing we want to discuss is what is called as the Q function, because we'll be using that quite a lot in our calculations. It's called as the Q function, and you need to understand exactly what this means. The Q function is the area under the Gaussian PDF's tail beyond a from some cutoff or a threshold value. For example, if I mark a line here, okay, let's say if I mark a line, let's say at 2. So the Q function is nothing but the area under the Gaussian PDF to the right of 2. And by the way, this Gaussian PDF, it extends till infinity. Okay, it becomes smaller and smaller and smaller, but it never becomes 0 until it reaches infinity. So the Gaussian tail goes on till infinity. So this area here is called as the Q function. So we'll denote that area here is called as the Q function of the Gaussian PDF, which has a certain standard deviation, and the cutoff point that we choose to compute the area. So we are computing the area to the right of 2, right, from 2 to infinity under this Gaussian PDF, which is centered on 0. So we'll write that as Q of 2 by sigma. In general, if we choose any voltage level, any value of V, let's say I choose another value, let's say something like this, and if that was V, okay, if we call that as, let's say, some V which is close to like 1.4 masalan, then this entire area would become Q of V by sigma. We call this as the Q function, which is nothing but the area under the Gaussian PDF to the right of some threshold, which we would denote as V. The threshold is V. Okay, I'm just going to mark this off. Okay, to the right of some threshold V. But the important thing here is that it's the area to the right of some V, which we can write as Q of V by sigma, when the Gaussian PDF is centered on 0. It should be centered on 0. If it is not centered on 0, we'll need to shift it and bring it to be centered on 0, and then determine what is that cutoff point, and correspondingly we will find what is that Q function. Now the importance of the Q function is that we will be using this in computing the error probabilities in our analysis later. So you should have an idea as to what the Q function means, and we can compute the area either by integrating under the Gaussian PDF, but since it's such a standard function, we have these values available as a table, so we are going to use the table to check out the values for the Q function and use it in our calculations. Okay, so the Q function is the area under the Gaussian PDF to the right of some threshold, which we denote as V, given that the Gaussian PDF is centered on 0. Okay, or not when, let me rephrase that, with the Gaussian PDF centered on 0. So it has to be centered on 0. The next observation that we make with regards to the Q function is that since the Gaussian PDF is symmetric, the area under the Gaussian PDF from, let's say, 2 to infinity, this area here, is the same as minus infinity to minus 2. So the area over here so if you mark this area here, that would be the same as Q of 2 by sigma. And if we choose any other value, for example, the general V that I took, which is close to, like, say, between 1 and 2, right? So if it was from here, and if I had to mark out this area, this entire area till infinity, then that is the same as Q of V by sigma, right? Because this is just the area under the curve. So whether we do the integration from V to infinity or from minus infinity to minus V, it would give us the same answer because of the symmetric nature of the Gaussian PDF. So if we had it, say, now minus V here, minus V, so from minus infinity to minus V, this area is Q of V by sigma, and similarly from minus infinity to minus 2, we can write that as Q of 2 by sigma. So we have a table available for computing the area under the Gaussian PDF as the Q function table, which we will use in our calculations. So that's another observation that you should know. Sometimes we might end up during our analysis where we want to compute the area on the negative side, and by exploiting the symmetric nature, we can translate it to the positive side, because the negative and positive side are mirror images about the mean value. So this area here is the same as this area over here, so we can just use the Q of V by sigma for minus V by sigma as well, right? So we'll exploit this property of symmetry in the Gaussian PDF to compute these areas from the negative side to and bring it to the positive side, and we can have it from the table. Okay, so again, this is useful in computing the error probabilities for the received signal. So when we have a received signal which has been corrupted by Gaussian noise, we need to observe the received signal and make some decision as to whether that received signal is representing a binary 1 or a binary 0. And most of the times we would get it correctly, but occasionally there would be some errors. And then we are interested in determining what is the probability of error, and the objective of the decision process at the receiver is to minimize the probability of error. So if we transmit, say, 1,000,000 bits, we want to make sure that out of the million, the number of errors is very, very small. Typically, we are talking about, say, 1 bit out of 1,000,000 bits is having an error. So that's like 10 power minus 6. So the error probability should be 10 power minus 6 or even lower. Okay, that depends on the application. If you are talking about, say, voice communication, the error probability should be 10 power minus 6 or even lower. But if it's like high definition video or ultra high definition video, then we need error probability which is even smaller, like 10 power minus 15 or 10 power minus 20. So we need to have our receiver processing designed in such a way that makes the error probability very, very small. It's almost close to zero. It's so small, like 10 power minus 15 or 10 power minus 20 for most practical cases. Okay, so we will see how we can develop techniques to make a decision regarding the determination of the bits that are being received, and then we'll also see how to analyze and get an expression for the average probability of error, and we'll do that for the binary case where we have only 2 voltage levels, as well as for the emery case where we have multiple voltage levels to represent symbols. Okay, we'll discuss all of these in the next part of the video.